Imagine standing on a beach watching the waves roll in. You think you understand what's happening. Water is moving, right? But then you look at light, and suddenly the common sense of the universe falls apart. What Richard Feynman uncovered isn't just a physics fact, it's a glitch in the matrix. It's the realization that light doesn't just travel from A to B, it explores every possible path in the universe simultaneously to get there. It's a story of how nature is fundamentally crazy, and if you aren't shocked by it, you haven't understood it yet. The concept of the path integral, or what I like to call the sum over histories, is perhaps the most mind-bending realization in the history of physics because it fundamentally shatters our concept of cause and effect. In our everyday lives, we assume that if we throw a ball to a friend, that ball follows a singular, predictable trajectory through space. We see the world through the lens of classical mechanics, where an object moves from point A to point B along a unique path defined by the laws of motion. However, when we zoom down to the level of a photon, the very fabric of reality starts to look like a hall of mirrors. Light does not simply pick the most efficient route and stick to it. Instead, the quantum mechanical reality is that light explores every imaginable path between 2 points simultaneously. This isn't just a metaphor for the complexity of light, it is a literal description of how the universe operates at its most fundamental level. To truly grasp the absurdity of this, you have to imagine a photon traveling from a star to your telescope. Conventional wisdom says it travels in a straight line through the vacuum of space, but Feynman's discovery tells us that to calculate the probability of that photon arriving, we have to account for the possibility of it swinging behind a distant galaxy, looping around a planet, or even traveling to the edge of the universe and back. Every one of these paths contributes to the final result. In the quantum world, the particle doesn't have a history. It has all possible histories at once. We represent these paths as little arrows or vectors in a complex plane. Each path has its own stopwatch that spins as the light travels, and the final position of the arrow depends on the time it took to travel that specific route. When you add all these millions of tiny arrows together, the ones that deviate wildly from the straight line tend to cancel each other out because their timings are all over the place. This cancellation is the only reason we see light traveling in straight lines in our macroscopic world. The straight path, we observe, is actually just the result of a massive cosmic interference pattern where the paths near the shortest distance reinforce one another, while the crazy paths effectively delete each other through destructive interference. It is as if nature is a giant accountant, constantly summing up an infinite number of possibilities to decide what we eventually perceive as a simple event. This implies that the empty space between two objects is not actually empty. It is teeming with the ghosts of every possible movement that could happen. We are living in a reality that is built upon a foundation of infinite possibilities, and the common sense physics we see is just a very thin crust on top of a churning, chaotic sea of quantum behavior. The most haunting part of this discovery is that it forces us to abandon the idea of local reality. If a photon is truly smelling every path in the universe to get to your eye, it means that the behavior of light right here is intimately connected to the geometry of the entire universe. You cannot isolate a single beam of light from the rest of space because, according to the path integral, that beam is interacting with everything. This led to the development of quantum electrodynamics, a framework that treats these interactions not as certainties, but as a series of probabilities represented by diagrams. These diagrams aren't just doodles. They are a rigorous shorthand for the infinite sum of paths. We are calculating the amplitude of an event, which is a fancy way of saying we are measuring the weight of all those combined histories to see which outcome wins. Despite the mathematical perfection of this system, there is a profound philosophical gap that remains unfilled. We can sit at a desk and crunch the numbers to predict the behavior of light with a precision that is staggering, yet we cannot explain the mechanism of how a single photon knows to consider the entire universe before it lands. It suggests a level of interconnectedness that defies our standard logic of time and space. We are forced to admit that the universe is not a machine made of gears and levers that move in a sequence, but rather a calculation of possibilities where every part of the system is aware of every other part. This discovery didn't just give us a better way to do physics, it gave us a glimpse into a world that is far more mysterious, expansive, and ridiculous than we ever dared to imagine, proving that the more we know, the more we realize how strange it is to exist at all. When we talk about the probability of a photon, we are stepping into a territory where the very ground of classical certainty gives way to a shimmering, uncertain mist. In our day-to-day experience, we expect things to happen for a reason, and we expect that if we have enough information, we can predict exactly where a projectile will land. But light plays a different game entirely. When a single photon is fired at a detector, we can never, ever say with absolute certainty where that specific bit of light will end up. We can have the most expensive equipment in the world, the most isolated laboratory, and the most brilliant minds watching the experiment, and yet the individual photon retains a stubborn, fundamental right to be unpredictable. This isn't because our instruments are leaky or our brains are small. It is because nature itself, at its most basic level, is not a clockwork machine. It is a game of chance that follows rules we can calculate but never truly visualize. This brings us to the core of the mystery, which is the transition from the individual to the collective. While the behavior of a single photon is a complete gamble, the behavior of a billion photons is incredibly precise. We can calculate the probability of where light will land with a mathematical accuracy that is almost frightening. We use these little mathematical arrows to represent the probability amplitude, and when we square the length of the resulting arrow, it gives us the odds of a photon hitting a specific spot. It is a perfect system of bookkeeping. We can tell you that there is a 30% chance of a hit here and a 5% chance there, and if you run the experiment 10,000 times, the light will fill those patterns exactly as predicted. The math is flawless, yet it leaves us with a hollow feeling in our chests because it refuses to explain the why behind the individual choice. The struggle for the human mind is to accept that we are living in a universe of chances rather than choices. We want there to be a hidden variable, some secret internal mechanism inside the photon that decides its path before it even starts its journey. We want to believe that if we just look closer, we would see a tiny steering wheel. But every experiment we have ever conducted suggests that there is no such thing. The photon doesn't decide until it arrives. This forces us to confront a reality that is fundamentally probabilistic. It means that the world is not a sequence of events following a rigid track, but a series of overlapping possibilities that only collapse into a single reality at the moment of interaction. We are looking at a world that is inherently fuzzy, a place where the logic of either-or is replaced by the logic of maybe until the very last millisecond. There is something deeply humbling about the fact that we can master the math of probability without understanding the nature of the entity we are measuring. We have built our entire modern world on this. Our transistors, our lasers, our computers, all based on a set of rules that describe the probability of particles moving. We are like people who have learned to win at a casino every single time by studying the odds, but we still have no idea how the dice are made or why they tumble the way they do. We have become incredibly proficient at manipulating the how while remaining completely blind to the why. This gap between calculation and comprehension is where the true beauty of physics lies. It is an admission that the universe is far more sophisticated than our intuition, and that our role is to observe the dance rather than to demand that the dancers follow our rules. Ultimately, the probability of a photon tells us that the universe is not made of stuff in the way we think of stones or bricks. It is made of events and the likelihood of those events occurring. When you look at a mirror, you aren't seeing light bouncing off a surface in a simple mechanical way. You are seeing the sum total of billions of individual probabilistic events all happening in concert to create the illusion of a solid, predictable reflection. The fact that such chaos on a microscopic level leads to such order on a macroscopic level is the greatest miracle of the physical world. It suggests that order is not the absence of randomness, but the result of it. We are floating on a sea of uncertainty, held up by the sheer mathematical consistency of chance, and the fact that we can even begin to describe this with our little equations is nothing short of a triumph. The logic of nature is something that often feels like a direct insult to the human ego because it refuses to conform to what we consider sensible or intuitive. When we dive into the world of light and quantum electrodynamics, we are forced to check our common sense at the door. Common sense is, after all, just a collection of prejudices we have built up based on our experience with large, slow-moving objects in our daily lives. We expect things to make sense. We expect causes to lead to effects in a straight line, and we expect a thing to be in one place at one time. But nature has no obligation to be understandable to us. It operates on a logic that is fundamentally absurd from our perspective. Yet it possesses a mathematical beauty and a consistency that is far more rigid than anything we see in our macroscopic world. This absurd logic is the bedrock of how everything in the universe actually functions when you get down to the brass tacks of the subatomic level. When we look at how light behaves, we see that it follows rules that seem almost like a joke played on the observer. For example, if you want to understand how light reflects off a mirror, the logic of nature says you have to consider not just the middle of the mirror where the light seems to bounce, but every single part of the mirror, including the edges and the corners. In fact, you have to consider the parts of the mirror that aren't even there. To the human mind, this is nonsense. We see a beam of light hitting a specific spot and moving on, but the internal logic of the universe requires a much more complex calculation involving interference patterns across the entire surface. Nature isn't using a simple straight edge to draw the path of light. It is using a complex system of waves and amplitudes that overlap and cancel each other out until only the most probable path remains visible to our dull human eyes. This absurdity is best illustrated by the realization that light is both a particle and a wave, yet somehow neither at the same time. We want to put things into boxes because that is how our brains evolved to survive on the savannah. We want to say it is either a solid little bullet or it is a ripple in a pond. Nature simply looks at our boxes and ignores them. It behaves according to its own framework, where a photon is a probability amplitude that can interfere with itself. This means that a single photon can pass through two different holes at the same time and create an interference pattern on the other side. If you try to catch it in the act, it changes its behavior. It is as if the universe is shy, or perhaps it is just that the act of looking is an intervention that the logic of nature cannot ignore. This isn't a failure of our experiments. It is a fundamental law of how the world is put together. The mathematics we use to describe this, the arrows that turn and the paths that sum up, is the most precise tool we have ever created. It is the language of this absurd logic. We can predict the results of experiments to a degree of accuracy that is almost unbelievable. Yet the steps we take to get to that answer seem like madness. If you were to describe these steps to someone who hadn't seen the evidence, they would think you were a mystic or a fool. You are essentially saying that to find out where a particle goes, you have to assume it goes everywhere. But the proof is in the results. This logic, as strange as it is, works perfectly. It allows us to build lasers, to understand the stars, and to design the very chips that power our civilization. We have found a map of the territory that works perfectly, even if the terrain it describes looks nothing like what we expected. Accepting this absurd logic requires a kind of intellectual honesty that is rare. It requires us to admit that the universe is much bigger and much stranger than our ability to visualize it. We have to be willing to follow the evidence wherever it leads, even if it leads us into a place where up is down and here is everywhere. Feynman always insisted that if you are bothered by the fact that nature works this way, that's your problem, not nature's. The universe is not a comfortable place designed to make humans feel smart. It is a vast, intricate, and deeply strange puzzle that operates on rules we are only just beginning to translate. By embracing this absurdity, we stop trying to force the universe to be sensible, and instead begin to appreciate the raw, naked beauty of how it actually is, which is far more interesting than any simple story we could have invented for ourselves. The arrow formalism represents the peak of Feynman's genius because it took the most terrifyingly complex mathematics in the history of physics and reduced it to something a child could visualize with a clock. Before this, the world of quantum electrodynamics was a nightmare of abstract equations and infinite series that made even the most brilliant physicists want to tear their hair out. Feynman looked at this mess and realized that at the heart of light's behavior is a very simple geometric idea involving little arrows, or what we call vectors, in a plane. Every path a photon can take is assigned one of these little arrows, and as the photon travels along a path, its arrow rotates like the hand of a stopwatch. The speed of that rotation is determined by the frequency of the light, and the final direction the arrow points when it reaches its destination tells us everything we need to know about that path's contribution to reality. To understand how this simplifies the universe, you have to imagine millions of these tiny arrows being drawn for every single possible way a photon could move from a source to a sensor. If you want to know if light will actually reach a certain spot, you don't do a massive calculus problem. Instead, you just lay these arrows tip to tail, one after another. If the arrows are all pointing in roughly the same direction, they add up to a very long, strong arrow, which means there is a high probability of the light being there. This is what happens in the center of a lens or along the path of a reflection. The timings of the different paths are so similar that the arrows agree with each other, reinforcing the signal and creating what we perceive as a bright, clear beam of light. It is a visual bookkeeping system that turns the mystery of quantum interference into a simple game of addition. Image showing a sequence of rotating vectors being added tip to tail to form a resultant vector. However, the real magic of the arrow formalism happens when the paths are wrong or deviate from the path of least time. For those paths, the timings vary wildly. One arrow might point up, the next might point down, the next to the left, and the next to the right. When you try to add these tip to tail, they just keep curling back on themselves in a tight, messy little knot that doesn't go anywhere. The resulting total arrow is essentially zero. This is the mathematical explanation for why we don't see light taking the crazy paths through the corners of the room. It's not that the light doesn't go there, it's that the arrows from those paths cancel each other out so perfectly that the final probability of detecting the light there is zero. Nature is effectively a master of subtraction, using the phase of these arrows to prune away the chaos and leave us with the orderly world we think we understand. This approach allows us to visualize things that were previously impossible to see, like how a mirror actually works. We usually think light just hits the center of a mirror and bounces off at the same angle, but the arrow formalism shows us that light is actually hitting the entire surface of the mirror. If you were to scrape away the edges of the mirror in just the right way, creating what we call a diffraction grating, you could actually stop the wrong arrows from canceling the right ones. Suddenly, you would see light reflecting in directions that seem to defy the laws of optics. This proves that the arrows are real and that the interference is happening everywhere, all the time. By using these arrows, Feynman gave us a way to see the invisible machinery of the vacuum, showing us that the stillness of a room is actually the result of trillions of quantum arrows spinning and colliding in a perfect silent balance. The beauty of this system is that it doesn't require you to believe in a specific physical model of a wave or a particle. It only asks you to follow the geometry. It treats the universe as a giant computer that is constantly summing up these rotations to decide what happens next. When we use this method to calculate the interaction between light and matter, we get results that are more accurate than any other measurement in science. It turns the deep, dark mystery of the quantum world into a transparent, mechanical process of vector addition. We no longer have to wander through a fog of maybe and perhaps. We can simply draw the arrows, watch how they turn, and see the truth emerge from the sum. It is a triumph of simplicity over complexity, proving that even the most profound secrets of nature can be understood if we find the right way to look at the geometry of the world. The refusal to pretend is perhaps the most courageous and revolutionary aspect of how we approach the mysteries of light and quantum mechanics. In almost every other field of human endeavor, there is a pressure to provide a satisfying why or a comforting mental picture that makes sense of the data. We want to be able to say that light is like a wave in a pool or like a stream of bullets because our brains are hardwired to understand the world through analogies. But the fundamental discovery regarding light is that these analogies are not just incomplete. They are fundamentally wrong. When we reach the bedrock of reality, we find that the universe does not behave like anything we have ever seen in our everyday lives. The true hallmark of intellectual honesty is the willingness to look at the math, see that it works with perfect precision, and then admit that we still have no idea how to visualize what is actually going on. This state of affairs creates a profound tension in the mind of the observer because we are using tools we cannot fully explain to achieve results we cannot deny. We have developed the most successful physical theory in history, one that can predict the behavior of an electron or a photon to 12 decimal places. Yet if you ask what that photon is doing between the time it is emitted and the time it is detected, the only honest answer is a shrug. We can describe the how with staggering accuracy, but the how is just a set of rules for calculation. It is not a story. It is not a movie we can play in our heads. This refusal to invent a comforting story to fill the gap is what separates real science from mere speculation. It is an admission that the universe is under no obligation to be visualizable to a collection of evolved primates on a small blue planet. When we stop pretending that we understand the underlying mechanism, we actually open the door to a much deeper kind of knowledge. By admitting that the sum over histories and the rotating arrows are just mathematical tricks that happen to match reality, we remain humble in the face of nature. We avoid the trap of thinking we have solved the universe and instead recognize that we have simply found a very good way to talk to it. This honesty allows us to work with the absurd logic of the quantum world without being paralyzed by our lack of intuition. We accept that light is an entity that obeys a specific mathematical grammar, and we focus on mastering that grammar rather than trying to force it to translate into a language it wasn't meant to speak. It is a transition from a child's desire for a story to an adult's appreciation for the raw, unvarnished truth. This gap between calculation and visualization is where the mystery of the unexplainable truly lives. No one can explain why a photon considers every path in the universe, or why the probability of an event is the square of a little arrow's length. These are just the rules of the game that we have discovered. If you try to ask why the rules are what they are, you quickly realize that you are no longer doing physics. You are peering into the very fabric of existence itself. The refusal to pretend means standing at the edge of that abyss and being okay with the fact that we cannot see the bottom. It is the realization that the world is much more interesting when it is mysterious than when it is explained by a shallow analogy that doesn't actually hold up under scrutiny. We are observers in a world that is fundamentally beyond our common sense, and there is a tremendous power in simply stating that fact out loud. In the end, this discovery about light teaches us that the ultimate goal of understanding isn't necessarily to make things feel familiar. Sometimes the greatest breakthrough is realizing that reality is profoundly unfamiliar and always will be. We have learned to calculate the dance of light with a precision that would have seemed like sorcery to our ancestors, yet the dancer remains hidden behind a curtain of probability and interference. By holding on to this honesty, we protect ourselves from the arrogance of thinking we know it all. We remain students of a universe that is far more complex, beautiful, and ridiculous than we are. This isn't a failure of science. It is the ultimate success. It is the moment where we stop trying to make the universe look like us and start trying to see the universe for what it truly is, even if what it is remains a beautiful, unsolvable riddle.